Okay, so what we're going to do now is we're going to have some expectation examples. So we're going to go through some examples where we calculate the expectation. I'm going to use, I think, the examples I did from the probability distribution lesson, just to make life easier. So example 1. How many tails do we expect if, hold on, let's get some more light. If we flip 2 coins. So how many tails do we expect if we flip 2 coins? So what we're going to do is we have our, so x is going to be number of tails, and xpx is going to be, so we're going to make an xpx chart. So if we flip 2 coins, we could get 0, 1, or 2 tables. And the probability of getting that is going to be 0.25, 0.5, and 0.25. 0 times 0.25 is 0. I think I did those in red last lesson. This would be 0.5. 2 times 0.25 is 0.5. We add it up, and we get that the sum is 1. So that means if we flip 2 coins, we expect, so the expectation for the variable x, where x is the number of tails, is 1. We expect to get 1 coin. I mean 1 tail. Which mostly makes sense. Definitely makes sense. Now, let's say instead we flip 3 coins. How many tails do we expect to get? Now, I'm not really going to explain the probability column. That was from last chapter, or you could draw a tree diagram to kind of figure it out. If x is the number of tails, if x is the number of tails, we could have 0, 1, 2, or 3 tails. And the probabilities turn out to be 1 out of 8, 3 out of 8, 3 out of 8, 1 out of 8. Then we do the XPX. 0 times 1 over 8 is 0. 1 times 3 over 8 is 3 over 8. 2 times 3 over 8 is 6 over 8. I could reduce this, but very often in these cases, the denominator will be the same. So it'll actually make life easier if you don't reduce this. So, well, this could be reduced to 3 over 4. Don't really want to do that yet. 3 over 8. And the summation is going to be 12 over 8, which is 1.5. So if we flip 3 coins, we expect to get 1.5 tails. Now, are we actually going to get 1.5 tails? The answer, of course, is no. You're not going to flip 1.5 tails. That's impossible. You're going to flip 0, 1, 2, or 3. You're probably going to flip 1 or 2. But you expect to flip 1.5. Would you round that off? You would not. You know, just like the, it doesn't matter if you can't actually get that. Back when we had the wheel, I still have that wheel from the other one? Right. Back in the other lesson, when we had this wheel, the expectation was 750. It didn't matter that it couldn't be 750. The expectation was 750, and that's what it is. So over here, the expectation is we're going to get 1.5 tails, and that's the expectation. There's nothing else to say about that one. Okay. Example 3, I think we're at. How many pips do you expect if you roll a 6-sided die once? So what we could get with that So we could get 1, 2, 3, 4, 5, or 6. The probability of rolling a 1 is 1 out of 6. The probability of rolling a 2 is 2 out of 6. Probability of 3. This is all wrong. That's also 1 out of 6. This is also 1 out of 6. The probabilities are 1 out of 6 for everything. Then what we have here is XPX. That's what I was kind of doing in my head. I jumped ahead. 2 times 1 over 6 is 2 over 6. 3 times 1 over 6 is 3 over 6. 4 times that is 4 over 6. 5 over 6, 6 over 6. And if we add that up, we get 21 over 6, which is 3.5. So if we roll a single-sided die, we would expect to get 3.5 pips. Pips, again, are the dots on a die. That's what we would expect to get. Example 4. You roll 1d6. If it's even, you win triple the roll. If it is double, you lose the square of the roll. So like if it's double. If it's even, you win triple. If it is odd, you lose the square of the roll. So if it was a 3, you're going to lose $9. And X is going to be your money. That's going to be the change. So what we have is, I'm going to actually, so what we could do is we could, again, if we roll 1d6, we could roll a 1, 2, 3, 4, 5, or 6, just like we had before. But the thing is, in this case, that's not really the X. That's not the thing we're looking for. X is looking for money, and 1 is not $1, and 2 is not, doesn't give you $2. So this is not the X. What this is over here, this is kind of like an extra column. This is a this is the result, and the result is nice to see, but it's not really part of our XPX table. So we have our result, but then we still have our X, our P of X, and our X and P of X. So if the result is a 1, the value of that result is we lose. So what do? We lose $1. And if it's a 2, then we win triple. So that's going to be plus 6. And if it's 3, we lose 3 times 3, so we lose $9. And if it's 4, we win $12. If it's 5, we lose 5 times 5. So the result for that is negative $25. And if it's 6, we win triple that, and that's going to be 18. So these are the results, but these are the actual values of the results. The probabilities are still 1 over 6. And a name for this is actually a uniform probability distribution, so that the probability is the same actually across the board. And again, I'm going to so then to get the expectation, I'm going to multiply these, and I'm not going to reduce it. So that's going to be minus 1 over 6, plus 6 over 6, minus 9 over 6, plus 12 over 6, minus 25 over 6, plus 18 over 6. And I'm definitely going to calculator that one, because, yep. Minus 1, plus 6, minus 9, plus 12, minus 25, plus 18 is 1 over 6. So that's going to be, I think, positive 1 over 6. So the expectation here is 1 over 6. Now, what does that mean? It's kind of dollars, I guess. 1 divided by 6 is 16.17 cents, essentially. So what we have is, in this case, we expect to win $0.17 or 17 cents. So if we play the game once, we expect to win 17 cents. Again, are we going to win 17 cents? No, we're either going to, we're going to lose $1, win $12, lose $25, win $18. But overall, we're going to win 17 cents. Is this a good game to play? Absolutely, because every time you play, you expect to win a bit of money. If you play it 10 times, you would expect to win $1.70. If you play it 100 times, you would expect to win $17. So this game is definitely worth playing. But notice, sometimes the result is not the value. And I think the last equation, the last example I'm going to do, this is example 5 apparently. And again, I'm going to use one that I did before, a bag. It's going to feel like recalculating probability. The bag has 7 red and 8 blue marbles. We're going to draw 2 simultaneously. How many reds do you expect to pull? So from the last lesson, if X is the number of red marbles, so X is going to be, in this case, number of reds. From the probability distribution lesson, it should be, rather. And then the probabilities were 267, 533, and 0.2. And so the XPX is going to be at 0. That's 0.4. And this one is going to be 0.533. And we add all that up, and we get 0.933. So what does that number mean? What that number means is this is the number, X is the number of red marbles, and the expectation for red is 0.933. In this situation, we expect to pull 0.933 marbles. Now, how many marbles are we most likely to pull? We're most likely to pull 1. But we expect to pull less than 1. So we're most likely to pull 1. We have about a 53% chance of pulling 1 marble, but we expect to pull a bit less than 1 red marble. And that's essentially that. So I'm not going to post the worksheet immediately. I think what I want you to do today is to go through those lessons and try to understand the examples that I gave.